So folks, welcome to our last set of lectures on this dependence analysis and loop transformations. Just to give you a little idea of where we stand now in terms of the remainder of the topics for the rest of the semester. So we'll be finishing this in probably this week and early next week. We will do the last homework, which will be fairly simple, trying to end topics. It will not be long, I promise. I know that you have a project coming up as due, but this is just to give you practice of some of these concepts on paper and pencil, which are really important topics. So we'll do this last homework, and that will be the homework which will be due towards the end of the semester. And then finally, we just have a final exam, which I will talk a little later. But after this particular topic, then we have some machine-specific optimizations we'll get into. And for that matter, we'll brush up a little bit of register allocation. Some of you might have not done it. Some of you, of course, have done it as a part of 40-40. We'll brush it up and then we'll look at certain machine-specific optimizations based on register allocations. Typically, those are the important ones. And that will be the last set of topics. We'll cover some of them through some papers, which I will present, of course. We won't have any term papers or anything from your side there. So that will pretty much be towards the end of this 2-3 weeks of remaining semester, 3 weeks more precisely, I think. So let's get started on it, the topic that we were looking at, and we'll complete some discussion about the how to actually do the dependence analysis. I have put on some slides there, which we'll be going through. So in the last lecture, we were looking at loop carried dependencies and the levels at which they are carried and so on. And here was that example. You can see that the dependence is carried at in the innermost loop here. That is, the ordering must be preserved as far as that particular loop nest is concerned. But you can also see here that the outer two loops, I and j, there is no dependence which is carried through the in a loop carried sense. So in short, you can see that if you analyze the dependencies, the loop carried dependence, what really is happening is in the innermost loop, in a given iteration, first the write occurs to a given array element. The next iteration of k is when the value is really used. That you can see this dependence, and that's why the direction of the vector is less than. So the origin of the dependence occurs at a iteration which is lesser than the consumption, and it's a true dependence. It's a flow dependence, which is occurring here. So as long as we preserve that, we can parallelize the outer two loops, and we'll sequentialize the inner loop. So that will be the way this will be enforced. So in general, this is what is about the loop transformation. Let T be a transformation on the loop nest that rearranges the statements in the body of the innermost loop. Then T is valid after it is applied. None of the direction vectors for the dependencies with source and sink in the nest has leftmost non-equal to component that is greater than. So basically we had to make sure that we don't convert a dependence into this greater than dependence, because that just cannot exist. in the normalized sense. So if we convert it, we are doing something wrong in terms of changing the ordering of the original intent of the dependencies. You can, of course, this is applicable when you have a normalized loop. And in the normalized loop, you can see that whatever occurs, the loop always executes from going from a lower index to a higher index from, let's say, a lower bound, which is like 0 or 1 or 10. Typically, it's normalized to 1. So it starts at 1 and goes to, let's say, whatever is the upper bound, but it keeps increasing. And so the dependence, whatever kind of dependence it would, if at all it is there, which is loop carried. In the previous example, it was true dependence, but it could very well be that we have a read occurring before write, and so that would be dependence which is anti-dependence. So in the original loop nest, it will be either output or anti or true dependence. But its direction vector, if it is loop carried, will always be less than, because that's the order in which the things execute. So somehow if we transform that into a greater than, then obviously it's a wrong transformation. That is what this particular observation says. And just to note, as long as we preserve it, whatever transformation we carried out, if it's preserved as the dependence is preserved there in the original intent, then that's the valid transformation. So we should not be converting it into this. So let us look at it a little bit deeper. Reordering transformation preserves all level K dependencies if it preserves the iteration order of the level K loop. So, and then if it does not interchange any loop at level less than K to a position inside the level K loop, and if it does not interchange any loop at level at a level greater than K to a position outside level K loop. So what it means is this, that we got to make sure that we are trying to preserve the level K dependence, which is ordered by, so it can be a less than, or it could be equal to. Equal to, of course, is easy one because it's not really loop carried dependence. But if it is less than, then there are two possibilities here. One is the level K dependence is being carried by the loop nest is the actual dependence that is getting enforced in the loop. And this would be the case if in this previous example that we saw, here is the level 3 dependence, which is really the loop's source of dependence. However, if we modify this example, for example, and if in the J level, instead of equal to less than, here if we had equal to less than, then you can imagine that actually the dependence is not really carried by level 3, but level 2. And we want to be able to enforce level 2 dependence here. So if level 2 dependence needs to be enforced, which is carried by loop J, then we need to make sure that we don't disturb, or we don't do any changes to the J loop, so that maybe the direction of dependence is reversed and things like that. So that is what this particular the observation means that we need to find out what is which is the dependence carrying loop here. It need not be always the innermost loop. It could be an outer loop. So we had to start worrying for all these dependence carrying loops one by one, and we want to make sure that the dependencies are obeyed and not altered by carrying the transformation. So let me illustrate this using some of these examples over here, and then I will also look at this a little bit more in terms of other transformations that could occur here. So, for example, in this particular topmost level, have the dependencies from S1 to S2, which is less than in terms of the S2 depends on S1, which is because of the value of F here, which is being carried as a loop carried dependence, flow dependence. And similarly, it's also the same is the case in terms of the dependence for I, A of I. So this is shown here, and if we decide to interchange these two statements such that A of I plus 1 is equal to F of I plus 1 and F of I plus 1 is equal to A of I plus 1, you can see that we are able to preserve both of these dependencies because even though we change the execution order within a particular iteration, across iterations, you can see that we still have the dependence being obeyed there. So instead of, for example, if you focus on the dependence due to A, instead of occurring from the end of the iteration to the beginning of next iteration, this is occurring from the beginning of a given iteration to the end of the next iteration. And similarly, the F iteration is now occurring from the end of the first iteration to the beginning of the second iteration. But if you look at the iterations across which they are occurring, they remain consecutive ones, and therefore the ordering or the direction vector there is not really altered as far as the iterations are concerned. And so this is a legal transformation as you can see here. Now, if you go to the, if you had done some other transformation on this, there will be a problem, and that may not be legal because of the relative order not being preserved there. Let's go to the next example, and you can see here this is again a flow iteration dependence. And it is less than from a statement to itself. So in other words, we generate a reference in A space, and then after one iteration in I space, two iterations in J space, and three iterations in K space, we consume it in terms of the flow dependence. So if we you can see that in the lower part of the loop, if we run the loop as we did two things here. We did the changes in the nesting level here, J and K we have interchanged, but we not only did that, but we have run the K loop now in the reverse direction from 10 to 1. So in other words, higher order um, executions of K loop now occur for higher K values into the and then they keep decreasing from 10 to 1. So what has happened here is if you look at um, um, the um, um, the dependence here, originally the dependencies were carried out in the iteration space from all ijk values which were low to ijk values which were high, and the iterations which were per se the dependence happen to be really the I iteration. You can see that that is the case in the original loop nest. And even if we had executed, let's say, K iterations in a different order, we would have preserved the dependence because it is really being enforced in the I dimension because the other loop, the I plus 1 and I, if you look at this pair, the consumption of dependence does not occur unless we get into the next iteration of I. And the relative order of execution in the J and K dimensions, in fact, both, really doesn't matter because they will generate the writes in different orders, of course, but they will never touch the iteration of I, which is needed, which is I plus 1. So I hope you're getting this particular part, that in order for the flow dependence to really occur, we need to generate the reads for the A only after the writes for all I plus 1 iterations in the previous in the current iteration have finished. And that will be the case because regardless of how we execute J and K, we would generate again the writes in different ways. So for example, if J started at 10 and went down to 1, we would have of course done writes in a different way because we would have started with 12, then we would have gone to 11 and so on. Similarly about K, so even if we would have reversed the orders of the J and K and executed them in reverse, or we could have interchanged them and reverse as whatever is shown here, we would have done in a different order. But what we would not have done, even in that case, is we would have not done a read which is corresponding to the same array element as is needed for the I. And that is why the outer loop I is the one which is carrying the dependence in this particular case. And as long as we preserve it, you can see that we are able to generate all these different writes, maybe in different order, but then get into the next iteration of I, and that's where all the corresponding reads will occur and consume the values of A which are generated, and because of this transform is legal. So we are able to do interchange here for inner loops. We are able to reverse the order as long as we preserve the outer loop which is carrying the dependence in this particular case. In the previous example, there was the dependence carrying loop was K. So if we, for example, run it in a reverse order, there will be a problem. They will immediately reverse the dependence, which is less than currently will become greater than, and that will create a, instead of doing a flow dependence there, that will become an anti-dependence. So in short, as long as we do not alter the dependence carrying loops, outermost dependence carrying loops ordering, the inner loops could be changed because they do not really carry the dependence, and dependence is enforced by the outer loop. So that is what this thing says here, and this is the example. And the relative order, the reordering transformations preserve a loop dependent between S1 and S2. It does not move statement instances, and it preserves the relative order. It's basically what is important, as was shown there. So this is the loop independent dependence here, and you can see that we can change there the ordering again. Instead of going from 1 to 10, we can go from 10 to 1 down, and that's what is shown here. In the other case also, it is a loop independent dependence, and we could just change the order. That is another two-dimensional example. So now we should look at a case which is what I have been kind of talking about in terms of the direction vector across the level, and what do we do about that? If we have multiple direction vectors at the same loop level, sometimes we had to approximate those in terms of star. Star basically means that we have different dependencies which could have, for example, two different direction vectors. So which could be less than or equal to, and so on. So you can see that in the second example, S is equal to S plus A of I, we have a star. The main reason for that is we have an anti-dependence, which is going from the read of S to the write of S in the same iteration. So that's an equal to kind of dependence. But then we also have flow dependence, or a true dependence, across iterations. That is, that value of S is being used in the next iteration, and that is a less than. So we have two kinds of dependencies here. One is equal to, which is anti, and which is less than, which is flow. And that's why that is shown as star. So in similar ways, you can think of the other examples here. And then in such cases, we need to worry about these dependencies playing out as a direction vector or a distance vector across dimensions. For example, in this case, we have distance vector because the differences between the I vectors as 1 and the other one is 0, or the direction vector is less than and equal to. And in this particular case, you can see again that the direction vector which is carrying, or the dependence which is being carried here, will be in the I dimension, which is less than. And any transformation that we do, if it preserves it, then we will be fine. If we, of course, violate it, that will not be fine. So let us take this simple example and see what would be fine and what would not be fine in this case. So if we end up, for example, running the I loop. Let's take that example first. Instead of going from 1 to 3, if we run it from 3 to 1, what is going to happen there? So you can see that that will be clear violation of the dependence because in this iteration order 1, 2, 3, I is increasing, and that is generating the dependencies as flow dependencies. If we run it the other way, we'll have the higher values of I occurring first, followed by the lower values of I occurring later. And that will need to the dependence changing from flow to anti. So in short, we cannot disturb the I loop running it in different order because it will not enforce the dependence which is carried by that particular loop, and it will lead to a violation. Now, what about interchanging I and J loops? So if we interchange those, of course, we'll have to redo the loop bounds and other things, which we can do using some techniques. But if you can see that currently the dependence was being carried by the outer loop. Instead of that, we will be carrying the dependence in the inner loop, in the I loop, and that will also be fine. So interchanging, however, is a legal transformation in this particular loop. We'll have to manipulate the loop bounds, make J as independent variable, and all those things we'll have to worry about. But that can be tackled, making sure that our loop, which is still carrying the dependence, is I loop, which becomes the inner loop. So in this particular case of this particular distance vector, this is how the iteration space is being traversed, and the distance vector is I loop. You can see that in this particular case, the direction vector is less than. In other words, you can see that at a given point, what we are doing is we are writing into, let's say, A44, where I is equal to 4 and J is equal to 3. And then in the next iteration, we are actually reading this particular value. 4 may not be a good example here because that's an upper bound, but you got the point. So in the next iteration, you can see that we are reading in the I dimension, and in the J dimension, we are also going to read from that particular space. So that's why the direction vector is less than. And so in this particular case, you can see that the way currently the loop is, J loop is the one which is carrying the dependence from one iteration to the other in the innermost sense, and in the outer sense, it is the I loop. So if we interchange these loops, that will still be, because in that particular case, the J loop will be the one which will be carrying the dependence instead of I loop, which is currently carrying the dependence. However, in this example, you see whatever is going on is the dependence here, the vector you can see is less than greater than, and the dependence is being carried by the I loop, which is of course the outer loop here, as you can see there, because greater than cannot be the loop which is carrying the cannot be the direction vector. That is the actual generation of the dependence is borne by I loop, and then in the next iteration of I loop is when the dependence is being consumed. So it's a flow or true dependence that is being generated and it's enforced by I. So now if you interchange this though, then you can see that the greater than will become the outer loop and less than will become the inner loop. And that will be in violation of the dependence because it will not be enforced by the outer loop. So that is why there are certain vectors where the interchange will not be legal, and this is one of those, which is less than greater than. This will be legal less than, greater than, and greater than less equal to. So both of these kinds of dependencies are fine. However, the ones which was less than greater than is not really fine. So let me just quickly explain this in a whiteboard, and then we will see. Okay, so so if you have loop nests such as I1, I2 to IN, these are the index variables, and this is the body of the loop. And the kinds of dependencies that you can have could be something like this, equal to and less than, and then here it could be stars typically. So it doesn't matter, that basically what it means. So in this particular case, you can see that this dependence here could be less than, and this is the loop which is carrying the dependence, is enforcing the dependence per se, because of the reads and writes occurring in a particular order. So this could be an anti, this could be an output, this could be true, it doesn't matter, but this is the loop which is enforcing that. Now, as I put stars here, what does that mean? So the stars basically mean that this could be a less than, this could be either an equal to, or this could even be greater than. And depending on the vector that we are seeing here, we are going to have to make a decision in terms of where to enforce this particular dependence. So for now, let's not worry about, or let's not talk about these stars for now. And let's talk about these. So instead of enforcing this at the kth level, let's say if this is my dependence and it is occurring at the kth level, I could very well move this to an outer loop, move these into inner loops like that, and do an interchange here, and this could be something like equals over here. And now you can see that instead of enforcing the dependence at this level, the iteration occurring in the innermost level of kth nesting level, now it occurs at the top level, and the dependence gets enforced there. So this interchange is a legal interchange because of this reason. What about the other variants of these? Let's look at those. So let's say these were two equals, and maybe this was also less, and this was equals, and this was equals. So any combination of this, if this is moved out for the top, so we could have this like this. This is also fine because the relative order of reads and writes is maintained now by this guy occurring at the top level and this guy enforcing it at the lower level. Or we could in fact also have this. So the interchange, as far as these are concerned, is always legal because it gets enforced by the correct direction vector here, and therefore we are trying to now enforce it at maybe loop levels, nestings level 1 and 2 instead of at kth level. What is problematic, however, is now consider a direction vector which is like this. We'll just keep it simple for 2 dimensions, and the same generalizes this. So this, if this is this example, it is still legal because we are enforcing it through an I loop instead of through a J loop and so on. Whatever kind of dependence that is, and it could be, again, it need not be just flow, it could be anti-output, whatever that is. This is second possibility, and the outer loop was the one which was enforcing. The inner loop had no dependence. It was not a loop carried dependence. And this is also fine to interchange. Now the dependence will be enforced by the inner loop, but the iteration order will in the space will be still preserved. So this is also fine. What is problematic is this. And now you can see that if we interchange these two, the iteration vector will look like this. And it is not possible to enforce the dependence unless we reverse the order. If this particular vector gets ahead of any of these dependence preserving vectors like less than, if that is the case, that will be a problem. And this particular case will mean that if we do an interchange, the original dependence was enforced by the outer loop. Now the outer loop is enforcing a different kind of dependence here, and that's a problem. And in fact, it generalizes like this, that if there exists this type of a dependence at kth level, which is enforcing, and if there is any kind of direction vector over here at inner level, so this is my kth level, and this is my level which is some m which is greater than k, and if that occurs here, then the interchange is illegal. Okay, because this guy will not be able to enforce it. What about internally? This guy goes in any kind of direction, things which is before k, that is fine. So something like this, if this was level 1, let's say, and this was level 5, then it could very well be that this could occur in a direction vector as long as the enforcement is still is in place over here. So something like this would be fine, or even this, because the writes will be the read-write order will be maintained across the iteration space, mainly by this outer one, which is not going to allow any reads for the corresponding I value or whatever that thing to take place before it reaches that particular iteration vector. So as long as the dependence enforcement is not getting violated by the interchange, by moving this guy outside of that, one can do any permutations inside and keep it there, like even this. But if you move this, like in this particular way, and violate, and then the dependence enforcement is going in the inner direction, and the outer loop is going to change the read-write orders of the dependencies, and that is going to be illegal. So that is the care that we had to take. And then any vector, if we have it in a particular way, if we reverse the order of that index, then it is going to transform into a reverse direction like this. And that particular reverse direction should be okay as long as there's no loop carry dependence in that dimension. So suppose it is enforced over here, and you reverse the order of loop like this, you should be still fine because the enforcement is still done by the outer loop, which was the example that was. So this should clarify all kinds of different possibilities. And then we'll also look at some more transformations about these loops when we talk about more detailed some other loop transformations. The interchange is one of the most important ones, and basically it means that the enforcement, as long as we don't change the loop which enforces it, and if we change it, then still it enforces it in the same way, like in this case. So instead of enforcing it in the I dimension, if we interchange it, it's getting enforced in the J dimension, which is also fine. But if it leads to a direction vector change, like in this case, that's a problem. So we'll talk more about this when we also do the interchange and some other transformations, but here is an important aspect of why these direction vectors are very critical in and what we need to preserve in terms of loop transformations once we know them. Any questions about this? We can always revisit this once we are more in the loop transformation territory. But for now, I think what we'll do is we will worry about how to actually find the dependencies, which is a critical one. And as I said, there are several interesting issues which are at the heart of this. And I have put in two which I would like to go through now. And we'll revisit the transformations at some later point. Again, as I said, when we do the loop transformations in details. So the first one we are going to look at is this particular set of slides, which is what we call as Banerjee inequality or Banerjee test. And this is a very famous test in terms of what we are going to look at here, especially on the dependence side. So the problem remains what we have been always talking about, whether or not we should be doing reads before write, and whether or not there is any, within a loop's execution time, there is any overlap between the two. And that's the goal of dependence analysis. And as you can imagine earlier, what I had mentioned was you can enumerate the whole thing, and that will not be practicable. And we want to be able to find this using some simple analysis. And in that particular process, we'll have to introduce some approximation and then worry about how to keep the analysis as precise but safe, and all these issues will occur. So again, just to recap all these flow dependencies, anti-dependencies, output dependencies, as you have seen here. What we want to be able to do here, and through an example, is safe compile time approximation, which is really at the heart of it. So let's understand the safety issue here, and then we'll work on the techniques of how to find the information. So This is the limitation again of static analysis and imprecise information, and we really have to do it in a safe manner. So how does this work? So suppose a simple example here. We have a procedure which takes x and ij, and we have a reference x of I is such and such, x of j is such and such. The question is, of course, is there an output dependence here between the two, x of I and x of j? Now that really depends on the values of I and j. And if I is equal to j, then there is a dependence, otherwise it's not. And so the question is, what do we know about I and j, and what kind of information we can use here? So if we do some very rigorous analysis and we are able to somehow prove that interprocedurally that I and j are always, for any invocation of this f, I and j are always distinct, then we can rule that there is no dependence. But if we cannot prove for certain, even one instance of the call, for example, interprocedurally, then obviously we must assume that they might become equal, and we must assume that there is a dependence. Maybe there is no dependence in real execution, because I and j are always distinct. But if we are not able to prove so for every invocation of this f, then we had to assume they are equal. And so what is the downside? If we assume that they're equal, the downside is that there is a dependence, and we will not be able to execute x of I and x of j in parallel, and we will lose a parallelization opportunity. So in short, if we assume a dependence when it does not exist, we are okay. But if we assume that there is no dependence when there might be one, we are not okay. So conservatively, unless proven otherwise, we cannot assume that there is no dependence. We must assume a dependence conservatively. By default, we must assume a dependence, in short. That's the bottom line. And we will lose some optimization opportunity, we'll lose some parallelization, etc. But this will be, of course, safe to do so. So how do we get this type of information at the loop level? How do we generate the tests at loop level? That is basically the thing that we need to worry about. So going back to original ideas that we saw, which is in terms of the loop iteration space. So we have these loop and j loops, and they are doing a lexicographic order on the iteration space. As you can imagine, 1 executes before 1 2, that executes before 1 3, and so on. So in short, j loop is increasing. Then the I loop goes into the next level, which is 2 1 2 2, and 100 100. Finally, is termination. So we know that this is the order of execution in the iteration space, and this, as I mentioned earlier, touches the array space and generates these references in reads and write. So one possibility may be to enumerate all this and see how are the array indices being generated, and then generate a trace of those and just find out if there is a dependence and what kind of dependence exists in the trace. But obviously that will be very slow and very time consuming, and if there is something called as n, in this case it is of course fixed as 100, but how about some n, and we don't know the value of n. So there are all these issues which will jeopardize the analysis, and even if we know 100 by 100 loop space, it is not a practical method. So what we need to worry about is how to first formulate this problem, and then we'll see how to go about actually doing a solver or how to solve this particular problem. So you have here, as a generalization, a do loop 1 to n, and then we have a index into the array space x of f of I. So f of I is a function, is an integral function of I, which is the index. So simple value of f of I could be 2i plus 1, for example. It could even be I square plus 5, which will be a nonlinear function. Typically, all these functions are linear functions of the form of I plus 3 kind of thing. Now you have another function which is mapping the index variable, the loop index variable, to the array index using GI. So that's a read. So now we look at different possibilities here for flow iteration and so on. You can note that here the loop is already normalized, is going from 1 to an upper bound in an increasing manner. So if we had to find out the conditions for flow dependence from a write iteration to a read iteration, then what it must be is, first of all, both IW and IR must be within the iteration space 1 to n. So that's the first condition that is given. And secondly, the write must occur before the read. So IW is less than equal to IR. You can see that. And so this is the ordering that must be present for the dependence to be flow dependence. Because the read must occur in a iteration which is smaller than the write, and both must occur within the bounds of the do loop. The second condition, however, is that they must map to the same array element, and that is the value of f of IW is equal to g of IR. That enforces the second condition for dependence, that is, they must touch upon this. Now, to be most precise here, we should say here that there exist IW and IR such that they satisfy this, and such as they also satisfy the second equality. And so that gives us the condition for the flow dependence to exist. Similarly, the condition for anti-dependence is again some IG and IO iterations, which is IG is less than IO. They both occur there. And you can see that this IG corresponds to the iteration for the G function or the read, and IO corresponds to the X of f of I. So f of I0 is equal to G of IG, and therefore both of them must touch the same iterations, same array element. And finally, if you have two writes, I1W and I2W2, two iterations which write those, generate the two writes, occur again within this, and f of IW1 must be equal to f of IW2 in terms of the output dependence being there. So that formalizes these kinds of conditions. And again, the choice is there exists because we are looking at the dependence in the loop as a whole. So even it occurs in like just two iterations within the loop, one write and one read, we'll declare the whole loop as non-parallelizable. You will see that most of the time that is not the case. It will, if it occurs once, it will occur periodically and regularly for the kinds of functions that we are interested in, especially linear functions of the form 2i plus 5, 2i plus 2j plus 7, like that. You will see that if it does occur for some pair of I1j1, I2j2, it will not just stop there, but it will occur for multiple such pairs within the loopness. And so the dependence will be there throughout the iteration space at some repetitive periodic interval. But just the fact that it occurs at least once is sufficient for the dependence to be there. So now let's look at the dependence in multidimensional loops. And basically, we'll just take one case here, which is flow dependence, and we'll just extend whatever we saw to the flow dependence case. So we have here I1 J1 as the iteration which is writing into the X, and I2 J2 as the dependence as the iteration which is reading from the same location in X. So the condition is I1 J1 and I2 J2, both of them must be within the loop bounds, and I1 J1 must be lexicographically before I2 J2. Because this is a flow dependence or output dependence, true dependence or a flow dependence. And f of I1 J1 should be equal to h of I2 J2. You can see the corresponding dimensions of this array. So this one and this one should be equal, and g of I1 J1 is equal to k of I2 J2. And then similarly, we can define the other ones. So if it exists some I1, J1, I2, J2 like this, then we say the dependence exists there, and we cannot parallelize that loop. Typically, as I said again, for linear f's and g's and all these different functions with the array index functions of the loop, it will occur repetitively. Okay, so let's keep going. So we already looked at some of these legal and illegal stuff, so we'll not worry about this. But we must, as you know, compute some additional information, which is the direction vectors and so on. So one possibility to calculate whether or not the dependence exists, like what we saw in the previous example, is formulate this as a flow dependence relation, put these constraints, in this particular example, IW will be equal to IR minus 1, which is a write is equal to read minus 1. And JW is equal to JR plus 1. How is that coming? Because we are taking the first dimension here of X and applying it, comparing it with the first dimension on the read side of X, that's IR minus 1. And similarly, JW is equal to JR plus 1. And then we can have an integer program, and we can run the whole dependence relation to this 100 by 100 things, and then find out if the dependence exists. You can easily see here it does exist, and it will tell us that you should not parallelize this loop. The big problem is this enumeration. This IOP calculator and integer programs, they run enumeration, and it will be taking a huge amount of times, and so that's not a feasible approach. So by now you must have already seen that this is really an integer programming problem, that we are trying to seek here a solution to an integer program, a satisfying solution if it exists or not in the for IW, JW, IR, and JR. They are not any arbitrary values, because not only they are constrained by these bounds on I and J, and also, of course, the lexicographic relation there, but by themselves, so these are iterations. So each iteration is, of course, an integer value. So if we had to solve these equations, IW is equal to IR minus 1 or JW is equal to JR plus 1 in a regular space, in a non-integral space, then the solutions are much easier, because all we do is we solve the simultaneous sets of equations in linear in the real space and find if they have a feasible solution or not. But that's not the case here, and so they must satisfy the integer relation, and these are constrained integers which they must satisfy the loop bounds, etc. And so the problem is a very hard problem and is an integer or NP complete problem. That is why the enumeration for getting exact solution, but enumeration is super expensive and is not feasible, and so therefore we must try and do something else here and try to get that. Now, one of the possibilities is that we try and compute here the dependence distance by manipulating the relations between IR and IW and JW and JR. And we can see that in this particular case, we can quickly get a distance vector, which is 1 minus 1. And therefore, from the distance vector, we can then get the full summary of the dependence that could exist in a loop nest. If we do so, we get the dependence directions, but sometimes this could be a problem. For example, in this simple example, x of 2i plus 1 is equal to x of I plus 1. And here we cannot get dependence distance because if you really look at the references, the distance itself is varying from the first 2iw plus 1 is equal to IR. So if we do this IW minus IR, you can see that that will lead to a varying distance. So since it's not fixed, we are not able to get it. We can get, however, the direction vector, and the direction vector is less than, equal to, or greater than, and we can do so by using IW minus IR, and whether that becomes a positive number, it may be varying number, but whether it is a positive number and or whether it is a negative number, based on that, we can fix the direction vector over there. And you can see that in this particular case, that will be a less than direction, because the distance will keep increasing, but it will remain at the less than level. Now, the problem of dependencies can be therefore summarized as either the distance in the J spaces and I spaces, or the directions in the I and J spaces, which is given in this particular way. Direction vectors can also is not any less problem, but it really means that we are adding an additional constraint here, and we are trying to find out a particular kind of dependence rather than any general kind of dependence. That's the only change of problem is there, which doesn't make it any smaller. Or any simpler than the original dependence problem. For example, if we had to solve the dependence problem for this loop nest, we could have simply without caring much about the dependence direction, we could have just simply done f of IW is equal to g of IR using rewrites, and whether putting the additional constraints IW and IR are both within the loop bounds. And so if we found dependence using these, In any kind of directions, we would have said, yes, there is a dependence here, and that stops us from parallelizing this particular loop. But now if we are interested, let's say in less than integer only for whatever reasons, then we will add additional constraint that tell me if there is a dependence or not when IW is less than IR. That is the iteration which does the write is less than the IR. Equal to means the iteration which does the read writes is the same. Okay, and then greater than, of course, that cannot occur because the loop is increasing. So we would have check the dependence by adding these two constraints and finding out if the dependence exists. But the original problem doesn't change by adding these constraints because we still have to enumerate under these particular constraints, and that will become infeasible again. We solve this problem in general for multiple nestings levels of the dependencies. We will enumerate it in a systematic way. We will start with the less than star. So that will be checking for less than or less than equal to or less than greater than. If none of these exists, then there is no less than star. Then we'll go for the two which are equal to, less than, and equal to. And then we'll rule out the impossible directions, especially for the normalized increasing bounds, which is equal to greater than and greater than star. Both are illegal, so we will not test for those. So that's how we'll carry out systematically this testing for direction vectors, which will give us some additional information. So how do we actually carrying things do the dependence analysis itself? We will try to then approximate this particular problem. Integer programming is the nature of this problem, and that's how we'll try to solve this particular problem by breaking them on a dimension by dimension basis, and we'll try to see if the dependence exists in each dimension or not. For example, let's take this simple example here. IJK loopness, and what we have is A, and the first index is 5, then I plus 1 and J is equal to A, N, and I, and K, and then whatever plus C. So if we had to analyze the dependencies here, you can see that the moment we can proclaim independence in one of the dimensions, and this is really important, the moment we can proclaim an independence in one of the dimensions of this pair of arrays, we don't have to carry out further testing. What I mean by that is, suppose we start with the first dimension and we have two things there. One is 5 and second is n. And if we can show that n will never be equal to 5, we have asserted that there is independence there. And so since 5 and n can never be equal to each other, there's no need for testing any other dimension because these two references will never ever become equal. If they cannot become equal in first dimension, they cannot obviously be equal at all. Now, this is one first dimension that we'll check. Now, we cannot sometimes prove independence in first dimension. Then we'll go to the second dimension and check if we can prove independence there. And if we can prove independence there, then we will simply stop there. And so this is the basis for what we call as dimension by dimension testing. It starts with the first dimension. If we assert and prove independence there, we stop there. If we cannot, then we have to assume that there may be a dependence. Again, remember that we may not be able to prove that there exists a dependence. We may have to actually assume conservatively that there may be a dependence. Like in this case, if we cannot prove 5 is not equal to n for all values of different values of n, then we must assume that 5 might be equal to n for some value of n and assume dependence. So in that case, we'll have to move to the second dimension and try to see if we can prove that independence and so on. And if we cannot prove independence, we have to assume dependence, and we'll keep moving down. And in that process, we'll carry out what is called as a dimension by dimension testing. And interestingly, depending on the types of things that we encounter, the dimension by dimension testing allows us to do very interesting types of special dependence analysis. So look at this particular example. In the first dimension, there are no variables, loop variables involved, neither I nor j nor k. And so we just have two constants, or symbolic constant n and then actual constant 5. And this is a case what we call as zero index variable subscript tests. That means there are no index variables participating in these functions. When we set up the dependent system, there are no functions of the ijk or surrounding loop index variables. And so that's why, since they are zero, we simply compare the constants. So how do we then decide on this, whether 5 is equal to n? Well, we'll carry out interprocedure analysis, propagate the value of n. And at this particular point, if we can prove n is not equal to 5, we'll declare independence right then and there. If we cannot, however, we have to move on and assume dependence. Now let's look at the next set of subscripts, I plus 1 and I. So in the second case, the subscripts in second dimension have both I in them, but are what we call as single index variables, subscripts. That means they both are coming from I, and we should be able to do some interesting testing based on that. And then there are subcases of this, what these subscripts mean. And in the third case, you can see that what is going on is we have two subscripts here which are coming from different variables, and so this is called as multiple index variable subscripts. Okay, now coming to the further cases here, which are interesting to sort of look at, is let's look at this example, ij, and ijk. So if you look at it in the first dimension, you can see that these i's do not occur in functions in second dimension or third dimension. So we can test for these I independently, completely independently. However, the j's cannot be separately tested from k's. You can see that's because of the j appears in both the second dimension as well as in the third dimension. And in the third dimension, we have k appearing as well. So we must analyze j and k's together simultaneously and solve them as a simultaneous system of equations in the integral domain. And that's why we will term them as coupled subscripts. And they will be very difficult to analyze because of the hardness of the problem. However, we can treat i's separately, and even they will be hard to analyze because of a different reason, that they are in the integral spaces. But the hardness of the j's analysis is because of their coupled or simultaneously true. So that's how we'll separate them into systems of equations, which could be solved independently, and systems of equations which could be solved in a coupled manner. And then we'll break them down into zero variables, zero index variables, or single index variables, which is just these i's, and whether the third one may be the multiple variables and could also be coupled across multiple dimensions and as a system of parallel system of equations. So zeros are very easy. Zero index variables are very easy to deal with. Single index variable, we'll see some more classification of that. And then we will talk about other cases in terms of doing some more specialized testing based on that. What in this particular case, we have IW and IR are the independent ones, and J's and K's are coupled ones. So we will try to solve those, as I said, using different things. Fortunately, many times we have coupled subscripts as a very rare occurrence, and many times we are able to simply solve them as independents, 80% of the cases. So let's quickly introduce the single index variables cases and look at it, and what are the kinds of things that are possible. So the most generalized subscript case in which occurs in the linear way is that the first subscript is a times I plus b, and the second subscript is c times I plus d. And so what we are looking for here is them being equal in IW and IR equations, in iterations rather. And so a times IW plus b is equal to c times IR plus d. And here we have what we call as a strong SIV subscript case, in which the coefficients of IW and IR are the same, that is A is equal to C. And if that is the case, we can reorganize these equations and say IR minus IW is equal to B minus D divided by A. Now you can easily see here that if both IR and IW are integral, then IR minus IW must be integral. And for that to be integral, B minus D must be divided by A. If it is not divisible by A, then we have a problem in terms of non-integer being equated to an integer, and that cannot have a solution to this system of equation. So the condition that is necessary here for the dependence to exist is that A must divide B minus D. That is one condition, but that's not the only condition. You can see that IR minus IW is also the distance between the read-write iterations, and that distance must fall within the loop bounds of I, otherwise there won't be any dependence. So that way we will check for B minus D divided by A if it is within the loop bounds that are there for the ith dimension. That is, if I is going from L to U, then B minus D by A must be within U minus L. So that's the first test. And so roughly about 37% of the subscripts are strong SIV, and that means their coefficients are same, A is equal to C. Many of them sometimes could even be equal to 1. Then the condition degenerates to B minus D falling within the loop bounds. But in general, that need not be the case for strong SIV subscript. A is equal to C, which may not be equal to 1. And so B minus D must be divisible by A is the first condition. And second is this particular quotient must be within the loop bounds, that is U minus L. That the dependence distance must fall within the bounds, otherwise loop bounds, otherwise there's no dependence between the pair. So that's where we can run the SIV test. I'm going to stop here. There's a weak SIV, which are all the special cases. And then in the next lecture, we'll talk about that, and we'll talk about a more generalized test when we have multiple index variables sitting there, and then we don't have any of the special conditions of them being equal or not. And we had to do the dependence testing in such a setting. So we'll talk about all this in the next lecture. So thank you, and then see you in office hours in case anybody has any questions on any of this.